We now begin examining nomenclature, which simply means naming, set of rules for naming binary molecular compounds. So far in our journey, we've talked about binary ionic, a metal to a nonmetal, where we consider charges. We talked about ternary ionic, still a positive and a negative ion, but one or perhaps even both of them would contain a polyatomic ion, those groups of atoms acting as a unit carrying a charge. We discussed the ate ending of those polyatomic ions. The next category, as seen on this slide, are called binary molecular compounds. Just as before, the term binary means composed of two elements. Molecular means this time they're composed of nonmetals only. Just to repeat myself, ionic, metal to nonmetal. Molecular, both of the elements are nonmetals. They live to the right of that border on the periodic table that separates the metals to the nonmetals. Since they are made completely different than ionic, they have their own set of rules for naming them. Binary molecular molecules that are composed of these nonmetals grouped together says the first, excuse me, I have a cold, so I'm apologizing right off the bat if I tend to clear my voice regularly. I'm trying to fight a head cold, so if I sound congested and clear my throat, please forgive me. It says we're going to write names of the first element in the formula. So I'm looking at the symbol of the element and simply write its name. Notice the element furthest left and down on the periodic table will be placed first in the nonmetal arrangement of our formula. And we use the full name of the element just as it appears on the periodic table. The name of the second element in our formula will end with an IDE suffix, just as with binary ionics, how the last name ended with "ide." So we simply say the first element as written on the chart, but the name of the second element will end in "ide." Remember, these do not contain ions. We're simply hearing the same ending, IDE. Molecular compounds share electrons in what's called a covalent bond. They are not made of ions where electrons are transferred from the metal to the nonmetal. So we say the name of the first element as it's written. We say the name of the second element, but change the ending to "ide." Now, to distinguish those subscripts, you will hear in the names prefixes in front of each one of the names to indicate how many atoms there are of each element. If the first element, and only the first one, has just one as its subscript, you may choose to leave the term mono off of that first element's name. Mono is the subscript prefix for the number 1. So, in a little flowchart down at the bottom of this slide, we hear a prefix followed by the name of the first element. We then hear a prefix followed by the name of the second element that ends with IDE. This is actually quite easy to catch on to, probably easier than the ionic compounds where we had to consider charges and crisscrossing to find subscripts to create an electrically neutral compound. We had to consider polyatomic ions versus monoatomic ions in the last category. I think this category is probably the easiest of all the compounds to name. Let's go through one at a time and just listen and just listen to the prefixes. If I have a subscript of 1, you'll hear mono. Di is the number 2. Tri for the number 3. Tetra denotes 4. Penta is for 5. Hexa for 6. Hepta denotes the number 7. Octa, nona, deca are 8, 9, and 10 respectively. These are the prefixes that we hear to denote the subscript telling us how many of each there are in a chemical formula for molecules. If we have a double vowel kind of tripping our tongue, drop the last A if the name begins with a vowel. Just to help roll off the tongue a little bit easier, you'll hear that we will drop off a double vowel sound to make it go a little bit smoother in our naming. Let's suppose we have the compound BF3. Now first, let's distinguish. Grab your periodic table, as always. I'm sure it's not far from you. Find boron on your periodic table. Boron is the symbol B. It's number 5 if that helps you locate it. Notice it's to the right of our border, making it a non-metal in its category. It's connected to the symbol F. Find that. It's number 9 to help you locate it quickly. F stands for the element fluorine, also a non-metal. Just to help you see this category, 2 non-metals covalently bonded to create a neutral molecule, a whole different way of forming compounds, so we have a whole different set of rules for naming them. Now it says we're going to name the first element just as it appears on the periodic table. The symbol B stands for boron. And again, note that the subscript here is just simply a 1. If the first element subscript has a 1, you tend not to hear that prefix mono. Mono must be there if the second element has a subscript of 1, but not for the first one. So monoboron is simply written as boron, the name of the first element. Now we name the second element, but I'm going to hear the ide. The name of the element fluorine turns to fluoride. Let's put on the appropriate prefix to tell us how many there are. Monoboron trifluoride, simply put, becomes boron trifluoride, dropping the prefix mono. Now remember, that's only for the first element, and any other subscript must be there in presence of a prefix there. Monotrifluoride. Simple. Say the name of the first element just as written, say the name of the second element, end it with "ide", and slap on the correct prefix, and you've just named yourself a binary molecular compound. Practice those skills with the following examples. Take the time to practice with your periodic table, looking up the names and formulas for the following compounds. Jot them on your notes. Start the video again when you're ready to check. Let's see how you did. The symbol N stands for the element nitrogen. The symbol O ending with "ide" is oxide. 1 nitrogen with 2 oxygens would sound like nitrogen dioxide. Notice the subscript 1 has been dropped from the prefix mono for that first element, just as it was in PCl5. P stands for the element phosphorus. Cl is chlorine, but naming it with an ide, it turns to chloride with the prefix penta. Reading that together, it says phosphorus pentachloride. Now the third example, I2F7. This one is a little weird in the fact that I have a double vowel. Well, actually, there's 3 vowels in a row. Diiodine, heptafluoride. But consider taking off any of those 3 vowels and the word just wouldn't sound correct. Diiodine tells me that the element iodine has a subscript 2. Heptafluoride tells me that there are 7 fluorines. So in this case, all those vowels must be kept just so the word sounds better. Dinitrogen pentoxide is a binary molecular compound. Let's turn those words into a chemical formula. Dinitrogen, simply let the prefix help you discover the subscript for each of those elements. Dinitrogen. Locate the symbol of the element nitrogen. The symbol, of course, is N. Locate the symbol for the element oxygen. Now hear the "ide" ending telling us it's the last name, but the symbol is O. Oxide comes from the element oxygen. Now listening to those prefixes, let the number come from the prefix into your chemical formula. The prefix di telling us 2, the prefix penta for 5. And putting it together, we get a chemical formula, N2O5, dinitrogen pentoxide. PowerPoint went a little slow there for me. N2O5, dinitrogen pentoxide. So very easy, just listening to the prefix to let you know how many of each there are. Now, very important, do not reduce the subscripts with molecular formulas. From the last lesson, always reduce the subscript for ionic compounds when we are writing positive ions hooking to negative ions, creating what was called a formula unit. Very important to write that in the lowest subscript ratio possible, or it would be marked wrong. But with molecules, we do not reduce the subscripts. The prefixes tell us how many of each there are. So in that first example here, dinitrogen tetraoxide, we can see that there would be 2 N's and 4 O's. We would not reduce those down. It's left as N2O4. Sulfur hexafluoride. The element sulfur, I do not hear a prefix, so I know it was a 1. Hexa tells me the number 6, and the element fluoride is the symbol F. Arsenic. Arsenic is number 33 on your periodic table. Find it and you can see the symbol AS. Excuse me. As2S3 telling us there's 2 arsenics for every 3 sulfurs. Every one of our binary molecular compounds ending with "ide." Say the name of the first one, just as it's written. It's the second one only that will end with "ide." Place on the appropriate prefix to denote how many of each, and those are the rules for binary molecular compounds. We have one more category of compounds, a family of elements known, or a family of compounds known as acids. Acids are a unique chemical family in chemistry. They're the opposite of bases, if you've heard of acid-base chemistry. Acids, of course, have their own unique chemical properties, grouping them together according by their pH levels. Since acids are a unique family, they actually have a specific set of rules for naming them as well. So we talked about binary ionic, ternary ionic, made of positive and negative ions considering charges. Third, we talked about molecular compounds, and the fourth category are acids. Acids are molecular compounds that form a hydrogen ion. Now that symbol H is from the element hydrogen, the very first element on our periodic table, when dissolved in water. Now acids and bases only exist in a water solution. So acid chemistry and base chemistry are all solutions. We do not name them as an acid if they are not dissolved in water. Only if they are AQ for aqueous, dissolved in water, will you hear the acid name. Just some chemical properties about acids that make them unique from other families. They tend to have a sour taste. Think of a lemon or a lime that has citric acid. Even an orange has citric acid. They're very corrosive. They'll dissolve many metals just by coming into contact. Zinc, iron, magnesium are active metals. Not so much the inactive metals like gold, silver, or platinum. Their formula, how do I tell if it's an acid? Their formula will always start with an H, the hydrogen ion. Now a lot of the rules apply here, thinking about the positive hooking to the negative to balance charges as we start to consider writing formulas of acids. So notice HCl and H2SO4 both start with an H. They'll be considered acids. This is a slide that shows how acids are so corrosive with many active metals. This is an atomic view of zinc atoms being dissolved into a hydrochloric acid solution. The symbols HCl stand for the acid called hydrochloric. Hydrochloric is sometimes known as muriatic acid, if you've heard of that. I know they sell it at Meijer like as the works, as a toilet bowl cleaner, that kind of thing. So zinc metal coming to contact with an acid, you start to see it dissolving into the solution. It's what's called a single replacement reaction, and hydrogen gas bubbles start to be seen. So definite evidence of a chemical change as acids and metals come into contact. Now, acids contain the hydrogen ion as its positive ion. The name of the acid depends upon what the hydrogen is hooked to. Now, the hydrogen is the positive, it's got to hook to a negative anion. Makes no sense that two positives would hook. Basic laws of electricity says like charges repel. Two negative ions would never hook. Again, like charges repel. We must have one positive hooking to one negative. Opposites attract, forming the compound. And if the first name of an acid is always hydrogen and it carries a +1 charge, again, check your periodic table. I bet you've written in that box hydrogen's charge. It's invariable. It's always a +1. So as an acid position of hydrogen, we consider what it's going to hook to as how to go about naming it. If the acid is binary, binary means two elements. The first one must be a hydrogen. The nonmetal that it's hooking to must be something from the periodic table, a monoatomic ion. F negative, Cl negative, Br negative, I negative. I'm just giving examples of negative ions over from the nonmetal side of the chart. Binary acids would have one hydrogen and some nonmetal from the periodic table. Ternary acids contain oxygen coming from a polyatomic anion. H plus is always the positive ion for an acid, and if I hook a hydrogen to a polyatomic ion, polyatomics we've noted before contain oxygen as part of their structure. So we'll have binary acids and what we call oxyacids if the polyatomic ion is in the last position. If acids start with an H, we'll learn how to name them based upon what the last name is. What is it hooked to determines how we go about naming an acid. If the original ending of the anion was an IDE, that's telling me it's monoatomic anion. The set of rules for naming binary acids say, start by the prefix hydro, followed by the nonmetal name ending with ic. Hydro, root word, ic. And then, of course, we would add the word acid. Hydro, root word, ic. Acid. When I say root word, I'm really just saying whatever the element off of our periodic table is that it's hooked to. HCl, hydrochloric. HF, hydrofluoric. HBr, hydrobromic. And so forth. Hydro, root word, ic. And then we put on the last part of the term, acid. If the original ending would have been ide, fluoride, chloride, bromide, we follow the hydro, root word, ic example. Here's an example of one we've just said, HCl. Notice it's aqueous. Acids are always in water solutions. H is always the positive if it's an acid. Anything that starts with an H other than water, that's the exception. H2O is not an acid nor a base. It's neutral. But here's an example. HCl starts with an H, so I'm going to name it as an acid. We would have named this, prior to this new lesson, we would have named this hydrogen chloride. Hydrogen chloride would be the name if this compound were not in water. But as soon as I see the AQ, I now name it as an acid. Hydrogen chloride becomes, and again, here the original ending was ide, hydro root word ic. Hydro root word ic. It would have been named hydrogen chloride. Now it becomes hydrochloric acid. Putting on that last word there, acid, lets the reader know it's in an aqueous solution. HCl, hydrochloric. Old way or out of water, hydrogen chloride. Hydro root word ic, we hear the acid name, hydrochloric acid. Binary compounds, usually ended in "ide" from the periodic table. Now we'll hear it hydro root word ic. What if our acid has a polyatomic ion involved? Polyatomic ions contain oxygen, so they're now referred to as oxyacids. If the original ending on the polyatomic ion was an ate, nitrate, sulfate, phosphate, acetate, hear those 8 endings from polyatomic ions? Now the rule says change the ending to an ic. Do not, and this is so important, do not use the prefix hydro. The only time we hear a prefix hydro is if it's binary, not for oxyacids. Oxyacids do not get a prefix hydro. If the polyatomic ending was originally ate, the ending gets changed to ic. If the polyatomic ion originally ended with ite, ite, nitrite, sulfite, phosphite, and so forth, the rule says to name it as an acid, change the ite to an ous ending. Find the original name of that polyatomic ion on your chart. Ate turns to ic, and ite turns to us, and we've named it as an acid. Let's consider some examples of oxyacids. I see a formula, H2SO4. This compound is not binary. It has more than 2 elements. I will not hear the prefix hydro. It's considered an oxyacid. I see the oxygen at the end. That tells me pull out the polyatomic ion chart and go to work finding the polyatomic ion SO4. On our chart, you're going to find SO4 in the center column, and it carries a -2 charge. SO4 -2, do you find it on your polyatomic chart? What's its name? Well, its name is sulfate. Notice it's a -2 charge. If hydrogen is a +1, and it always is that invariable charge of hydrogen, a +1, sulfate is a -2. How many hydrogens at a +1 are required to neutralize the charge of sulfate's -2? And you can see why in our formula the subscript 2 is written after hydrogen. It's there to balance charges. Now, if our formula H2SO4 started by identifying the negative anion, we found it on our polyatomic chart, sulfate. Remember the rule, ate turns to ic. If it had been ite, we know it was us, but this ended in ate. Sulfate. Now I know some of us might have been tempted to say sulfic, and that's okay, but eventually it will just sound right to us. We put the last syllable of the element back in for this particular example. The polyatomic ion sulfate, when it's named as an acid, becomes sulfuric acid. It says kind of an exception because it just sounds better to put it sulfic or sulfuric. I would take either, but knowing that sulfuric eventually will sound better to our ears as we learn this language of chemistry. Notice there is no hydro. It's not needed. It's letting us know it's an oxyacid. See, not hearing it is just as informative as hearing it. We know it's an acid because we said it's acid in the last name of it. So sulfuric acid, H2SO4. There are a few examples of elements, not many, but a few of them that we'll learn that puts the last syllable back in. Like phosphate becomes phosphoric acid. Here's an example. It's an oxyacid. Close by where we were just looking on the polyatomic ion chart for sulfate, if you look up just one from it, you'll find sulfite. Notice one less oxygen and 8 turned to ite. Notice the charge. That's why there's 2 hydrogens to balance electrically the -2 charge of sulfite. If H is a +1, sulfite is a -2. When I crisscross charges, we find our formula, H2SO3. Now that it's aqueous, we would have named this hydrogen sulfite if it were not an aqueous acid, hydrogen sulfite. But now let's name it as an acid. We do not hear the prefix hydro, never will for oxyacids. Ite turns to us, and we get our acid's name as sulfurous acid. Sulfuric, H2SO4, sulfurous, H2SO3. Getting some practice with ite endings lets us get quicker at naming our acids. Excuse me. When I look at naming, we had binary ionic, ternary ionic, molecular compounds, and acids. Those are the 4 major categories. Here's a slide that you should pause and practice your naming skills. Notice they all start with H. Follow the rules for naming them as acids. Practice with the pause and then start the video back up when ready to check. How'd you do? H2S is a binary acid. We know to start that with the prefix hydro. If I would have named this not as an acid, it would have been named hydrogen sulfide. That IDE ending says when it's binary, hydro root word ic, hydrosulfuric acid. HClO3 is an oxyacid. You went to the polyatomic ion chart, first column, little more than halfway down, you found the polyatomic ion ClO3 with a -1 charge. Chlorate is the name of that polyatomic ion. Chlorate, that ATE says, as we name it as an acid, ate turns to ic. Chlorate turns to chloric acid. And our last example, same first column on our polyatomic chart, skim down until you find NO2 carrying a -1. NO2 -1 is called nitrite, ite. ITE turns to us. Nitrite becomes nitrous acid. No prefix hydro unless it's binary. Oxyacids do not get hydro in front of them. Let's try the opposite direction. What if we hear a name and are asked to write its formula? Well, when you see the ending acid, right away you know it starts with an H. That's how we denote acids. So positive ion guaranteed is always H with its +1 charge. Always the starting element, a hydrogen ion. We write formulas as though they were ionic, considering charges. Even though hydrogen is a nonmetal and it's hooking to a group of nonmetals, technically speaking, these are molecular compounds, but hydrogen is just unique. It follows the trend of the first family, carrying a +1 charge. So just consider charges as though you were writing ionic compounds. If you hear the prefix hydro, you know it's binary, no oxygen involved. And remember, not hearing the prefix hydro is just as informative as letting you know polyatomic ions are involved. Not hearing the prefix hydro lets you know it's an oxyacid. And we look up the last name on the polyatomic ion chart. If you hear ic, you know the polyatomic ion must have originally ended with 8. And if you hear the ending OUS, us, then you know the original ending must have been ite, I-T-E. Okay, that's a typo on this slide. If the original ending is us, the polyatomic ion ends in ite. Ic came from 8, us came from ite. Hearing the prefix hydro lets us know it's binary. Not hearing the prefix hydro lets us know it's an oxyacid. Polyatomic ions involved. I'm going to quick take a drink of water. Sorry. Here's an example. Hydrosulfuric acid. Well, step 1, we know the symbol for the cation and its charge. Always, the symbol will be H+ for acids. Write the symbol for the anion in its charge. Well, the anion, notice that it's hydro. Hydro says that it's not a polyatomic ion. It's binary. What root word do you hear for the element? Hear that root word sulfur? We have to go to the chart and find sulfur and consider its charge. Sulfur lives right under oxygen. I bet you have, or you should pretty soon, write the charge right in the box as a -2. If H+ hooks to a -2 sulfur, considering the charges, crisscross, and what do we find? If H is a +1, S is a -2, 2 units of that +1 electrically balance the 1 unit of a -2, our formula looks like H2S, and we'll let you know it's aqueous with the little symbols AQ. Checking our work, we see hydrogen, 2 units of a +1, electrically balance 1 unit of a -2 to give a net charge of 0. Hydrosulfuric acid, H2S. What about oxyacids? Let's listen to carbonic acid. Now, how do I know it's an oxyacid right away? Because I don't hear the prefix hydro. Not hearing it is just as informative as hearing it. Carbonic acid. Well, as soon as I see that it's an acid, what is its first ion? Guaranteed. Well, we know it's going to be a positive hydrogen ion. What about the anion and its charge? I know it's an oxyacid because I do not hear the prefix hydro. What about listening to the end? Hear the ic? Carbonic. What original ending on the polyatomic had been turned to the ic? Well, ic came from ate. ATE must have been the original ending. So now I know the polyatomic name is carbonate. Go to work finding on your polyatomic chart carbonate and record its symbol. See how it's CO3? 1 carbon, 3 oxygens with a net -2. Carbonate, CO3 -2. How many positives are required to balance the negatives? Again, considering crisscrossing, the charge of -2 becomes the subscript after the hydrogen. 2 units of a +1 electrically balance the 1 unit of a -2. Carbonic acid. Those acids that are found in a can of pop, giving it its fizz. Carbonic acid, H2CO3. And checking the total charge, 2 units of our +1 hydrogen do indeed balance the -2 charge of a carbonate, giving us a net of 0. Aqueous carbonic acid, H2CO3. Ic came from ate. What about us? Here's an example, sulfurous acid. It's an oxyacid, I know right away, because I don't hear the prefix hydro. What do we now know that will be the positive ion, always for acids? Well, yes, it's the H+ ion. OUS came from the original ending, ite. Can you find on your polyatomic chart the polyatomic ion called sulfite? Us came from ite. We need to find sulfite. Do you see it? Second column of our polyatomic chart, halfway down perhaps, a little less than halfway, sulfite, SO3 minus 2. Consider charges as we think about writing our formula. How many positive compared to so many negatives to create an electrically neutral compound? Well, 2 units of a +1 hydrogen are needed to balance the -2 charge of sulfite. H2SO3 aqueous. Hydrogen sulfite, named as an acid, is called sulfurous acid. Out of water, hydrogen sulfite. In water, sulfurous acid. And notice when we check charges as a double check if our subscripts are correct, 2 units of the +1 hydrogen's charge do indeed balance 1 unit of sulfite's -2 charge. Hydro, root word ic, plain old ic, or us, the endings of acids. Try one more set. Pause the video and work through your examples. Please start when ready. Let's take a look. We know that all of them start with H, and H is a +1 charge. H with a chlorite. Us came from ite. Chlorite. Now we would have named it hydrogen chlorite. As an acid, chlorous acid. Polyatomic ion chlorite. Phosphoric. I know it's an oxyacid. I don't hear the prefix hydro. Ic came from 8. You looked up the polyatomic ion called phosphate. To the far right side of your polyatomic chart, you'll see phosphate. H3PO4, balancing charge. Hydro, root word ic. Hydro. Now it's binary. That tells me hydrogen is hooking to the element bromine. If you find right underneath fluorine, chlorine, there's bromine, that 7th family, it carries a -1 charge. Out of water, hydrogen bromide. Dissolved in water, hydrobromic acid. And again, consider charges just as we would with ionic compounds. Naming acids, those compounds that start with H, and whatever its last name is, will help us determine how to go about naming it. Friends, for the next part of our lesson, I'm going to pause here and let you gather some more materials. We're going to need definitely our calculators. We're going to be hitting some things on our calculator keys, and then also access to your periodic table. So when ready with those tools, let's start up again.